IT teams spend millions on secure service edge platforms like Zscaler ZIA, expecting a complete safety net. The working assumption is that funneling all outbound internet traffic through a central proxy guarantees total visibility and data loss prevention across the board. But modern communication tools operate differently. Consumer messaging apps and enterprise collaboration platforms introduce strict layers of privacy that a network proxy cannot simply peer into, creating a significant security blind spot. To see why, we have to look at the mechanics of inspection. This layered network flow diagram shows a standard web connection, like a user browsing X. When the traffic passes through Zscaler, the outer TLS layer turns green. The proxy successfully intercepts, opens, and inspects the traffic because the browser inherently trusts the proxy certificate. Now watch what happens when we apply that exact same inspection process to an application using end-to-end encryption. The destination changes to WhatsApp. The outer TLS layer still turns green. The proxy can intercept the transport, but the actual message payload sits inside a secondary container that remains unreadable in red. Deploying SSL inspection means Zscaler terminates the transport TLS session. It strips away the outer shell. However, the proxy does not have the specific application-level encryption data needed to read the content. The payload remains opaque. Intercepting a network connection and decrypting an application's payload are two distinct capabilities. Breaking the transport layer does not grant access to the actual message inside. The visibility problem expands when we move away from web browsers and look at native desktop and mobile applications. These apps do not rely on standard web trust stores. They use their own rigid authentication rules. Their primary defense mechanism is called certificate pinning. The application is hard-coded to trust only one specific, predefined digital certificate, and it actively interrogates any connection attempt. This animated diagram illustrates what happens when a network proxy intervenes. The proxy generates and offers its own substitute certificate to the smartphone application, attempting to establish an inspection tunnel. The application instantly recognizes that the substitute certificate does not match its pinned requirements. It triggers its defenses, flashes a warning, and aggressively rejects the connection. IT administrators are forced into a corner. They must either allow the application to break and drop the traffic entirely, or manually exempt the application. Exempting it creates a bypass lane, routing the traffic around the proxy entirely. End-to-end encryption combined with certificate pinning guarantees that any architecture relying purely on the network edge will have massive, unreadable traffic gaps. Before you can secure the traffic you cannot inspect, you need an exact accounting of what your network proxy is actually capable of reading. This matrix categorizes traffic. For HTTP and HTTPS, the proxy reads plain text, scoring green check marks for inspection and visibility. With certificate pinning, substitute certificates are rejected, failing both. Under end-to-end encryption, the proxy inspects TLS, but the payload remains encrypted, failing visibility. Applying a blanket SSL inspection policy across the entire organization accomplishes very little, until you map the specific protocol limitations of the applications your employees use. Once you map these limitations, you face a direct architectural dilemma. How should you handle the traffic your proxy cannot read? The first path, option A, is explicitly allowing the encrypted or pinned application by exempting it from your inspection policies. You retain basic network controls. You can restrict destination IPs, throttle available bandwidth, and identify the application being used. You also accept a total data loss prevention blind spot. Sensitive files, proprietary code, or regulated data sent through the app will bypass your scanners completely. Option B is configuring the proxy to strictly block all uninspectable or pinned application traffic outright. This creates a hermetically sealed network environment. No hidden, encrypted, or unverified data can successfully leave the perimeter. It also causes severe user friction and breaks critical business functions. One-to-one Microsoft Teams media calls fail. External client communications via WhatsApp are severed. Relying exclusively on a network proxy forces a direct choice between accepting data blind spots or impacting user productivity. Solving this gap without breaking the applications requires a strategic pivot, moving the security investment away from the network perimeter and placing it directly onto the user's device. Option C requires deploying endpoint DLP, endpoint detection and response, and browser security agents locally on the hardware. This data flow diagram illustrates why this works. The local security agent inspects the sensitive data before the application encrypts it for transit, or right after it decrypts it upon receipt. This introduces significant architectural complexity. IT teams must manage local endpoint agents across thousands of devices and integrate them with additional cloud security tooling. But endpoint control remains the sole method to achieve payload visibility without compromising the application's required end-to-end trust model. This reality requires a shift in how you evaluate and purchase security platforms. Asking a vendor if their proxy can decrypt HTTPS is a deeply flawed question that yields incomplete answers. The mathematically correct question you must ask is, at which specific encryption layer can your tool obtain plaintext? Build an encryption visibility matrix prior to deployment. Plotting WhatsApp, X, and Gmail reveals exactly where data loss prevention works and where it fails. Complex apps like Microsoft Teams split traffic. Standard chat is inspectable, but one-to-one media uses end-to-end encryption, bypassing proxy DLP entirely. Mapping out this matrix is a mandatory step. It exposes the exact network blind spots before a single policy goes live. Your final architectural decision depends heavily on your industry constraints. For banking, healthcare, and government agencies, the risk tolerance is near zero. Regulated environments must pursue option B, aggressively blocking consumer encrypted apps. The defensible approach is mandating strictly managed, inspectable corporate communication tools. General enterprise environments face a vastly different reality. They prioritize agile collaboration and fast user productivity alongside baseline security. These organizations pursue option C. Network inspection alone is insufficient, so they must layer their architecture with robust endpoint DLP and strong identity controls. A mature security architecture recognizes that forward proxy SSL inspection removes one layer of transport encryption. It is a highly valuable tool, but it is not a universal solution for the modern application layer.